Hello, everybody. I hope you can hear me. As already was said, I'm talking about network coding. And I have heard a lot of nice problems that you will face when you go to 5G, right? If you go to 500 billion devices, how do you want to manage them? There was already the question, distributed or centralized? Centralized, planned, good luck, right? So you have to find a solution that can deal with the dynamics of networks, with the dynamics of channels, dynamics of content and users, and still be able to get to the end user. So I'm not so much thinking about spectrum. I'm just thinking about something that is called network coding. I will show you what it is. And I would like to show you that we have a coding scheme that fits nicely for storage and for communication. And I often talk to people that think that there are two different things. But a packet that is now on the fly and is buffered in a switch, is it storage or communication? So where is the line? And if you think about software-defined networks, where we can really create agile edge caching, then we don't have any more these two worlds. We will have a condensed plasma, where you have packets on the fly, stored a little bit on the edge cache, on devices, on the base station, wherever you think about it. So when you have then different possibilities to get the content, where do you get it? And how can you face this dynamics? That's the talk about, right? I also would like to start with a small history in networks. I mean, if you haven't seen all this nice, colorful slides now, this sounds maybe a little bit boring. But nevertheless, I want to prove a point, right? Where do we come from? And why do we have to be disruptive? Why is, if you make 5G as a linear extension of 3G, 4G, whatever, good luck, right? You will get some improvements there, but you will not answer the needs of the users. And we'll also introduce this, what I call the key technology network coding, and it's especially this random linear network code. So there are codes that are based on randomness, on chaos, right? Why are they good for us now? And what makes it different to other codes that are out there? A little bit about the implementation of network coding. Is it really mature that you can put it into your products? And then maybe map this to distributed storage, transport, and software-defined networks. So if you think about communication, and you start with a telegraph, strictly point-to-point, right? Then we move to the real networks, the telephone networks, and they started to undergo evolution from fully meshed star technologies to hierarchical networks. So a fully meshed network here, as you can see, is nice to start with, but it's not scalable. If you think about 500 billion nodes and you want to have a fully meshed network, also this is not a good idea. So they moved this and said, oh, let's be smart, let's make a star. That looks like this, right? And the reason that they have to think about something different is this tower burned down. So you can imagine how long it takes to bring up the tower again and build up all the cabling here. So what they had was the telephone system circuit switched. All of us know this stuff, right? Circuit switched, voice oriented. And then somebody, I just quote here Paul Barron from the 60s, he said, let's change that. So there was a network that brought money, and somebody came with the idea and said, we move circuit switch to packet switch. So this is not an evolution anymore, this is a revolution. So we are disintegrating the path or the circuit. Now we think about packets, okay? And thinking about packets has some advantage if you think about reliability. So here you see a fully meshed, and you can think about not only one way, and here you see if this fails, you will have problems to repair that. But here you have different ways of doing that, right? Now, if you think about the internet, and internet, I mean, you can think about the fixed internet, but all the other meshed topologies we have, Wi-Fi mesh, Internet of Things, machine to machine, all of them, they do one thing, they build one path here. And that's not a good idea if you think about security, because an eardropper could sit here and just listen to your stuff. Also from the performance, it's not very good. And nowadays, people start to think about maybe we should use more passes, right? If you've heard about IETF, multi-pass TCP, they want to have maybe create more passes here. And if you think a real good mesh network is the brain, right? If you take your finger and your hammer and you smash on your finger, it's not a good idea. But if you do that, you will see how multipass will go on in the brain. Because of what? Reliability. But in our technical world, we don't use multipass so much. All wireless mesh routing protocols, or is our AODV Batman, one single pass. The internet, one single pass. If you don't trust me, go trace route to your favorite server. It's always the same. So what we want to propose here is to say, let's move from here to something that is exploiting the multipasses, but even have more flexibility, more dynamics. If you think, for example, dynamics, wireless mesh networks like Internet of Things, machine to machine, device to device, but even storage, right? Storage is not a big thing like Amazon server in Virginia anymore. That will now melt into our networks. We will have different sources where the content can come from, and that goes then into content-centric networks. And my definition of 5G would be then to say, okay, reliability is something, throughput is something, but also delay, we have heard it before, security, how to make this thing secure, and how to deal with the complexity. But because what we are doing here, we are changing from a store and forward, very stupid way of taking packets, sending packets, to compute and forward. So we have to compute something. And this adds complexity, and how can we deal with that? So again, moving from here to here, again, that would be a revolution. And I strongly believe that 5G has to be a revolution and not an evolution. We introduced this concept of compute and forward. And what we are doing here is we are disintegrating packets. So remember, first, disintegration from circuit to packet. And now we want to get rid of packets. We are building representation of packets. And this gives us new ways how we can propagate this through the network. Now, how is this done? Now, a little bit of math. I don't want to go too deep into that, but what you see here is you will have a bunch of packets, and you will run this bunch of packets in an uncoded way over a coding matrix. Everybody who knows something about coding knows this is the standard way of doing it. And what we normally do is we say we want to plan this matrix very carefully. Reed Solomon, there would be somebody who's thinking about how to do it, how is the network, and starting to build the network. What we do in random linear network code is we just fill it up with random numbers. And we can show it's equally good. And this randomness in the elements here is represented by some bits. So we say also field size or field elements. Now, the easiest way is just to say this element can be 0 and 1, but to have more granularity in the randomness, you will have here higher bit fields, higher field sizes, we say that. And the higher the field size is, the better the performance of the code is, but also the complexity starts to grow. Now, when you have that, when you have decided on your coding matrix, of course you get out the coded packets here, and you can use them. There's another feature of random linear network codes, they are rateless. You can create as many packets as you want. Just to reveal, coding, source coding, for example, takes information and gets away of the redundancy. Channel coding will add redundancy when needed. What is added or removed here? Nothing. So if all your packets have 1,000 bit here, they will also have 1,000 bits on the other sides. So what we do is we just find another representation. Nothing else. When we build these coded packets, what we also will transport are these coding coefficients. So in contrast to everything that is end-to-end, like telephone graphs, telephone lines, Reed-Solomon codes, and all the other codes, this code is not end-to-end. This code can be used or recoded at any node in the network. So every time you face some dynamics and you have to adapt, you don't have to go back and do something. You do it at the nodes where it is necessary to do that. And as I said already, when you get the packets, you have to make a Gaussian elimination of this matrix, which is in performance-wise cubic. That is a little bit more complex than just forwarding packets, of course. But if you later will see, we have some implementation where you will see that this cubic factor, you can make your software design in a way to make this A very small and the B a little bit bigger. So the impact of the power to the 2 is bigger than the cubic one. Okay, that is the way how we do it. And there are some more features in the code. So, of course, we can take our random code as a block code, as Reed-Solomon. I think everybody has heard about Reed-Solomon. We just say we take a bunch of packets, we code them, and that's it. Then we would be equally good to the other codes, right? But what we also can do is, you have seen this matrix. And in this matrix, we can design the matrix to go through this matrix like a corridor. First of all, we can just say we don't have to wait for all the packets to come in. So if I'm a base station and there's a live feed and packets come in, the first packet I will just forward. The next one I can code together with the first one, and the third one, and so on. So I can do coding on the fly. And if I get some feedback, I can even close this window, as you can see here. So I will have a very beneficial behavior if it comes to the delay. So coding originally will always give you a certain delay, an extra delay. But here you will get coding performance with nearly no delay. This has not only good things for a live video feed, also for TCP. Over years, over decades, people have tried Reed-Solomon with TCP. It did not work so well. Now there are some implementations called coded TCP that give you some gains between 2 and 10x. The other thing I already told you is that every node in a network can do this recoding step when it is needed. So you can actually recode data when it is needed. And I will show you an example where this is beneficial. Last but not least, this coding is also working with uncoded packets. So you don't have to change your network from day one on. You can integrate random linear network coding enabled devices after a while, and they will also talk with uncoding with devices that cannot code, right? So here's just one result without going into detail, showing the over-the-top transport. What we did is we built an Android client, TCP, and something in Amazon Cloud, TCP. It's a proxy. Everything in between is transparent for us. And then we say we want to have a normal TCP connection, or we want to have a coded TCP version. What you see here is a measurement campaign in California with over 1,000 data pairs, where a pair has already 100 measurements, where the people really try to get to different servers in the world globally and retrieve data. And this is the gain, what you see for coded TCP. Sometimes TCP was faster because we do tests in serial, so stuff can change. But if it was fast, it was really only marginally faster. This one, there were some outliers here. But if you see, you always can gain if you combine TCP and the coding. Now, this is on transport layer, right? Can we do more? Of course, if we think about a more relaying type, right? What you see here, we have a source that has 64 packets that would like to convey the 64 packets to the destination. And the source is just broadcasting. The relays try to get what it can get, but also the destination with 20% probability will get a packet. Here with 60% they will get it and then do something. And the question is, we do coding here and coding here, let's say on application layer, and now we do the coding here at the lower layers. So if we just do store and forward, you can see it here, you will need around 100 packets. This is the inverse cumulative density function, but this is the mean value. You see, you need 100 transmissions from here to make it happen. This is just an impact on the field size that I talked to you before. Not so big. Big is if you allow them to recode. So they just take the data and recode over it, and you reduce it nearly by 30 packets. There's no signaling whatsoever between these relays. So if you have a deterministic end-to-end code, you would need to tell the other one what you are doing. If you want to have a scheduled approach, you have to talk to each other. If you think about cars on a highway in Germany, 200 km/h, how can they organize something? The only chance they have is to give them some means to do something without the signaling. And this is what we're doing here, right? No signaling at all due to the recoding, giving you a huge benefit. Now, I have worked with some of my students from 2006 on a software library that is called KODO, that is really making this technology possible on different platforms. You can have it on Android, Raspberry Pi, iOS, Windows Mobile, Windows, whatever you want to say, different compilers, also addressing different devices. It should run on servers, right? If it's on servers, we need some hardware and multi-core support. It should work also on sensors, FPGA support, and so on. So originally, it's implemented in C++. You can download it. It's free for research. If you have intend to make some commercial product out of it, you have to pay for it. And what you have also is the so-called bindings. So now students, or even in the companies, people can make very quick demonstrators using Python. Python is very easy, right? 10 lines of code, and you can use the whole powerful library through some Python extensions. Here, that was for our Sony friend, a Sony Xperia, and we are running here the KODO library on top of that, and we look, can we do something in improving the performance of such codes? So we are already quite high here, as you can see, with over 10 megabit per second. But what you can see here is we can work on the matrix, and what we are doing is we are shooting some zeros into this matrix. If you remember your math class, you know, a fully ranked matrix was always hard to solve. Some zeros were always nice to do something with that. So we are shooting in zeros intentionally to make it less computational complex. So if we would not have any zeros in our matrix here, the coding speed would be 20 megabytes per second. If we do a lot of zeros into the stuff, we can go up to 300 megabits. So we gain 1 order of magnitude. And if you have higher matrices, the magnitude, there are even 2 orders of magnitudes to gain. So what we are doing is we are looking into the coding, how to make it very efficient, right? How to make it powerful so that you can run it. Another thing that we are looking at is, this is a new type, is we are taking this network codes and we try to make a new family. It's called FULCRUM. What we can do now is, I told you this matrix has these elements, so the complexity. What we try to do is, we want to have a fluid assessment of the complexity. So my mobile phone is very powerful, 4 cores. So it's not as powerful as an Amazon server, but compared that I'm the only user on the phone, there's a lot of computational power for me. So at my phone, I can use a very high field, where the other phones, the low-end phones, all your gadgets and sensors, they can use with a very low complex, a binary field. Even the switches can use a binary field, because there are millions of streams. They don't have so much time, right? And then there are the servers that may add a little bit higher complexity to the whole stuff on the source level. So what we are having here is storage and transportation with the same code with different complexity levels, right? So it's a very versatile code. If you then look at the application fields, one of them is, for example, channel bundling. If you think of a mobile phone, you have Wi-Fi and you have LTE. There are now some attempts to use multipass TCP, showing great results in the internet. But if you use multipass TCP over 2 connections, not my results, that are results of the multipass TCP group in IETF, they are saying if I have Wi-Fi and LTE, there's no benefit for them in taking both channels. They should take the better channel, okay? Because the dynamics are so high. And they need to schedule for that. And with random neural network codes, you don't have to do that. You code your data, you shoot over both ends as you like, and whatever comes on the other side, fine, right? Peer-to-peer networks is something very interesting. There's not only for files, there's IETF WebRTC, so real-time communication browser to browser. How can you make this exchange of data very efficient without planning? Network coding. Point-to-point with delay constraints, TCP I showed you. Distributed storage, I will tell you something later on. device-to-device communication is one of my favorite topics. I'm coming from there. I think we started with Samsung in 2000 to work on device-to-device. And we try to understand how can we share data among us users, because we are moving, right? And if I have to signal what I have and you have, we are running into this Panini problem, right? The collector problem. We always exchange data that we already have. With network coding, we will always exchange data that makes a difference. Reliable multicast for the stadium and all the wireless mesh work. These are the application fields. And I give you now some of our very easy, accessible examples. And it shows, first of all, how easy it is to integrate, but also what is the power behind network coding. First, we had one student that took the KODO library and he said, I want to build my own kind of Dropbox, using Dropbox in different areas. And you take your data and you code it, and then you plug it into the different clouds. So first of all, you don't have to pay for it. For the student, it was very important not to pay, accumulating the free stuff. You can think about when you code it, it's inherently secure. Don't put all your eggs in one basket, but just put a little bit of data here and there. Nobody can access. I will tell you something about this. And then, of course, what is with the download speed? How quickly can I get it back? Now, if you see at the security, we have 6 packets here. We can generate 8 coded packets. We do 2 coded packets in each of the clouds. We have 4 clouds here. And I need to get access to 3 of that. So the NSA who's sitting here will not find anything useful. Not even here, not here, not here. Even if they crack 2 and understand this connection, not possible to do that. What we have done then is to say, how are the clouds behaving? So first of all, we thought the clouds are more or less homogeneous, right? But there are dynamics in the clouds itself. What you see here is we have 4 different clouds, and we gave them all the information and said, send me the data as fast as you can. And you see there's one cloud coming very quickly with a lot of packets. Also another cloud quickly, but only a few packets. Another one came late. And this will change over the day. So you cannot schedule for that, okay? And this is what shows here the download time it takes to retrieve from 5 different clouds. This is the network coding approach, and this is the just the diversity and scheduling approach. And you see from the variance here that sometimes the scheduling can be very good as the other one, but sometimes it can be very bad. And for information retrieval, that is very bad. Even for users, right? If you promise this service, everybody who's above that will call you and say your service is not working. What you also see is you don't have to put all the data into the clouds. You can reduce it to a minimum. And if you say, okay, I take only less than the half in each of the clouds, a potential hacker has to hack 3 of your clouds, but still you would have a very nice speed up in getting your data. So it provides you here security and also a better performance. Now, what happens if your cloud provider like Dropbox says, I don't want you anymore here, and kills you? Or if you have a very agile system where storage is going up and down. So what you have here is you have 20 information packets, you code it into 40, you put it into 10 different clouds, each containing 4 coded versions. And then you kill 3, and then you open up 3, and you ask how many parents can fill this up. With Reed Solomon and all the others, what you need to do is you need to get enough information to recode the missing one. But what is if you don't have enough, right? And here you see these are the parents, and traffic costs you money. Most people forget about this. So you want to reduce the traffic towards these 3 buckets, but also the overall storage, because here I made 40 different pieces, but it could be even more. And what I will show you here is the performance of a no-coding, Reed Solomon, and network coding when it comes to more dynamics. And you will see now here something, we call it an ice block, and the reliability you always want to have on the top. And of course, traffic and storage should be minimized here and here and here. And you see now what happens over the rounds. We are killing, refilling, killing, refilling. In the no-coding, after 20 rounds, it's really going down, right? Even if you oversign by a factor of 10, you cannot hold it. Reed Solomon is going down a little bit less, but also here you need already oversign by 5 times your storage to have some chance to get your data back. Network coding is quite stable, right? You can now find the optimal point for storage or for traffic, what is important there. So in Reed-Solomon, in order to guarantee it, now you should call back and say, wait, everybody, I need to clean up my storage. In this one, it can be very agile. We are using this currently to build up storage based on your Facebook friends, on mobile phones. They are not always reliable, available. So we can deal with a lot of fluctuations using this kind of, I see you already, but. Last thing, if we think about all the flexibility in the networks, right? One of the things is software-defined networks. Before that, we had only store and forward. Now, these different nodes in a software-defined network, you can do something with that. So I can work on the buffer. That means I can use it, misuse it as a storage, edge caching, or I can use the buffer and recode over the buffer, making it more efficient, creating multi-passes and so on. This is our testbed in Aalborg University, 16 different PCs with some hardware support and servers. And we think about how to implement most of the stuff, and network coding is already running together with OpenFlow. Okay, as a conclusion, make it short, right? The future networks, right, they have to deal with this higher dynamics, right? We have new things. It's not end-to-end anymore. Therefore, we cannot use end-to-end codes anymore, right? So we have more mesh type, more dynamics. Then I also, as I pointed out, the storage will be in the network, right? It will be very close to you. Maybe if you retrieve a video, it will be in the network by your neighbor, anywhere, right? And I think, or I hope I've shown that network coding is a viable solution to address all of the described problems, right? And by the way, we are using the same code for transportation and storage, right? I think this is quite remarkable. That means we don't differentiate from the code anymore what is what, okay? That was my last slide. Thank you very much.